Hey everybody, in this video we're going to be using single variable calculus techniques to prove the formula for the volume of a cone. It's actually a lot simpler than the volume of a sphere. So we're going to start with what we use to form a cone. So if you think about a cone, right here, this is a solid cone, so we can fill it in and call it solid. It's formed by taking a triangle, this triangle right here. We'll actually put it in a different color so you guys can make sure to see which triangle is getting rotated. Here, we'll use red for this one. So it's as if you take this triangle and you rotate it about this axis. The axis we'll put in black. It's a good color for the axis. So it's as if you rotate about that axis, and that forms our solid cone. And so if we represent this in a Cartesian coordinate system, we can draw a line that goes through the origin. So we'll choose this line. Now it didn't have to be upward sloping, it could be downward sloping. This is an arbitrary choice for a line. But the equation of this line is y equals mx. There's no b terms because the b is 0 because this line goes through the origin. So given that it's mx, now we need to define some limits. So a cone has a radius r, which is here, and a height h. Those two quantities define our cone. So if we're going to revolve about the y-axis, our height is going to be on the y-axis. So it's going to be going up to this h, and this is going to be going to r. Also, because it's r and h have define the points of a point on the line. Sorry, we know that h equals mr, and we'll be using that later. Now what we need to do is we need to do our disk method. So we're going to be taking these smaller and smaller rectangles right here and rotating them on the y-axis till we get disks. And what we're going to end up forming is something that looks a little bit like this. And this starts to resemble a solid cone. Right. So now the last thing to do is carry out the integration. So our limits are going to be we're going to take it in terms of y, so it's going to be from 0 to h. And we're going to be taking disks, which are given by the equation pi r squared times the height. In this case, the height is dy. And in this case, r is going to be given by the x value. So it's going to be pi times x squared times dy. Now we're going to take this pi to the outside, and we can't leave this in terms of x since it's in terms of y, with respect to y. So we're going to convert this, so it's going to look like integral from 0 to h. Remember, the pi is on the outside now. And x, if we look at this y equals mx equation, x is just equal to y over m. Square it, dy. Now, since the m is a constant, we can actually just take it on the outside. So we get pi over m squared, right, because this whole quantity is squared. Integral from 0 to h, y squared dy. And this is a simple integral to evaluate. It's simply, if we go up here, 1/3 y cubed evaluated from, if we look at our limits, 0 to h, so 0 to h, and that ends up being 1/3 h cubed. Now don't forget the pi over m squared that was out here, so that becomes, if we go over here, pi over m squared times 1/3 h cubed. And now we're almost done. We just need to make sure we can transform this m. So remember here we have the equation h equals mr. That means m equals h over r. That means m squared equals h squared over r squared. So we're going to put that in. So when we divide it by h squared over r squared times 1/3 h cubed, that is the same thing as pi r squared over h squared times 1/3 h cubed. And the h squared on the bottom and two of the h's on the top cancel out, so we're left with just h. So in the end we get pi over 3 r squared h, which we know as the equation for the volume of a cone.